Assalamu alaikum wa rahmatullahi wa barakatuh. My name is Turki Al-Utaybi and I will introduce our project, which is the structural design of an Islamic center in Neom. The project was prepared by Muhammad Al-Qahtani and Abdul Salam Al-Fadri also. At first, what is Neom? Neom is a vision of the Crown Prince of Saudi Arabia, Mohammed bin Salman. It is the centerpiece of Saudi Arabia's 2030 vision to grow and diversify the Saudi economy and position the country to a leading role in the global development. NEOM is being funded and driven by Saudi Arabia, but it's also a mega international project, which is also funded by some other countries and other investors. This is where the city will lie. It is located at the crossroads of the world. 30% of the world population will be able to reach Neom in less than 4 hours. Approximately 10% of the world's trade already flows to the Red Sea, flying into Neom's new airport. The method used to design was the strength design method. In this method, the reinforced concrete structure is designed beyond the elastic region. The working dead load and live load are multiplied by a factor of safety. The section designed to fail at a factored load. Failure at a factored load means the section exceeds the elastic region to ultimate strength, then failure. The benefits of the strength design method is it produces a much more economical structure. It is much more flexible compared to the working strength design method. The scope of our project is limited to analysis and design of the structure subjected to dead load and live load. This design project considered 4 constraints of design. First is to design an Islamic center in Neom, Saudi Arabia. Second is to solve the social problems in the community. Third is to design an economical safe project. Fourth is to design an environmental friendly project. This is the whole plan for the project. As we can see, it's the mosque down there and the library. This is the cross section of the mosque. Now I will talk about the slab design. As we know, there is 2 different types of slabs. The first one is two-way slabs, which the load transfers to the whole 4 sides of 4 spans, and the other type is one-way slabs, where the load transfers to the longer span 50-50. This design, which is a two-way slab, as we can calculate, is less than 2, so we design it as a two-way slab. Then we determine the thickness from the ACI code table. We got it at approximately 12 inches. Then we calculate the effective depth. We got it at 11 inches. Then we determine the moment coefficient for the negative moment and the positive moments in the long and the short spans. Then we calculate the ultimate load, which is the slab load, and the live load is from the ASPC code. Then we got the ultimate load at 0.532. Then we calculate the moment. The first moment we calculate is the negative moment in the short direction. We got at 18.4. Then we calculate the Rn to get the rho. To calculate the area steel required, we got at 0.3762 square inches. So we use number 3 bar at 3.5 inches of spacing. Then we check for the maximum spacing. We have it at 3.5. It's less than 18, which is the maximum. Then we calculate the design moment. We got it at 18.34, which is less than the ultimate moment, which is okay and safe. Then we do this the procedure for the negative moment in the long direction. We calculate the negative moment in the long direction then we calculate the Rn to get the raw minimum. The raw we get raw minimum because the Rn is lesser. It's less than 160. 106. Then we calculate the area steel required. We got it at 0.2376 square inches. So we use the number 3 bar at 5.5 inches spacing. Then we check for the then again we check for the maximum spacing. We got it's okay because it's lesser than 18, which is the maximum. Then we do for the design moment, we got it at 11.69 kilofeet, which is less than the ultimate moment at 6.29, which is safe. Then we do for the positive moment in the short direction, which is slightly different because we calculate we have the coefficients for the dead loads and the live loads. It's not like the previous two. So we get the ultimate load at 10.29, sorry. Then we calculate the Rn. We get at 94.49, which is less than 106. So we use the raw minimum to find the required area of steel. We have it at 0.2376 square inches. So we use number 3 bar at 5.5 spacing. Then we check for the maximum spacing. It checks out. It's okay. It's safe. Then we do the the design moment. We got it at 11.73, which is more than the ultimate load, which is safe. Then we repeat the previous procedure, but for the positive moment in the longer direction, we get the maximum, the ultimate moment at 3.99 kilo over feet. Then we calculate the Rn. It's the minimum, so we use raw minimum to calculate the area of steel. We get at then again 0.2376 square inches. So we use number 3 bar at 5.5 inches of spacing. It checks out with the it's less than the maximum maximum spacing. Then we see we calculate the the design moment. We got it at 11.73, which is more than the ultimate moment, which is safe and economical. This is the reinforcement details, and this concludes my part of the presentation. Thank you.
Bismillahirrahmanirrahim. My name is Mohammed Al-Qahtani, and today I'm going to explain the design of beams and design of columns. First of all, design of beam. We need the slab details to design the beam, which is the thickness of the slab and the self-weight of the slab. Calculation of the load. We need to calculation of the load. Dead load for slab from one-way slab, and calculation of the dead load from wall. We need the wall thickness, which is 8 inches, equal to 20 centimeters, and wall height, which is equal to 4 meters, and the total dead load of the wall. Then we calculate the total dead wall of the wall, and calculation of the dead load from self-weight of the beam. We need the dimensions of the beam. We find the dimensions of the beam by these two formulas for the thickness and height. Then effective depth, which is h minus cover, and self-weight of the beam. Total dead load of the beam equal total dead load of the slab plus total dead load of the wall plus self-weight of the beam. Then calculate the life load from the slab to beam B1 and B2, B1 B2, which is equal 105 pound square feet. Then calculating the life load by this formula. Total combination load of the beam, which is equal to WU 1.2 dead load plus 1.6 life load, which is equal to 3.906 kilo per feet. Then we calculate the maximum negative moment and positive maximum positive moment at the middle. Now we will calculate the maximum negative moment at the support, which is equal to ultimate moment. Then we calculate after ultimate moment, we calculate the nominal moment, which is ultimate moment dividing by 0.9, which is 5. Then Rn, calculating Rn and As 1. The capacity of the beam mu1. After we finding mu1, we see if mu, which is ultimate moment, is bigger than mn1. If it is bigger, design as a double reinforced beam. If it is not bigger, smaller, design as a single reinforced beam. Now we find mn2. Then check the compression steel. After checking the compression steel, the value it is the steel has yielded. Then we calculate AS dash, the required, and AS. After we finding AS dash and AS, we find the flexural design of the flexural design strength of the beam. After we finding the flexural design, phi mn is bigger than mu, which is okay. Positive moment at the mid of the span, it is the same of the negative moment at the support. Then we have the shear force design, which is equal Vu. After we finding the shear force, we find the maximum spacing provide to minimum stirrups area. We provide the 3 rules for the spacing and see which one of them is smaller. Here the smaller one is 7 inches, which is equal to spacing at 7 inches center to center. Of course we use stirrups number 3 bar. And this is the cross section of the beam number 1 and 2. Bismillah ar-Rahman ar-Rahim. Now I'm going to explain design of columns, which is equal total dead load for beam 3-4. Bismillah ar-Rahman ar-Rahim. Now I'm going to explain column of Bismillah. Bismillah ar-Rahman ar-Rahim. Now I'm going to explain column design, column number 4, which is equal total dead load for beam 3-4, and life load, which is equal total combination load of the beam, and total dead load for beam 3-4B, which is under the beam number 3-4 exactly. Now calculating the BU, which is equal to WL over 2. After finding BU, we find the maximum moment at support, which is equal 168.36 kilo feet. Then external load of the column, which is B actual, and MUX, which is equal to 0, and MUY, which is equal, we just calculated 168.36 kilo feet. Column dimensions, we need the area of the column, effective cover, which is equal to 3, effective depth, and effective depth, which is equal to overall depth, which is h, minus 2 multiply effective cover, which is equal 10 inches. Self weight of the load of column. Self weight, which is equal ag multiply L multiply rho C, which is density for the concrete. طيب, total dead load combination after finding self weight of the column and computing the design value for uni-actual bending. Slenderness ratio, we need to find the slenderness ratio, which is equal to less than 12, which is okay, and determining eccentricity value, which is equal to 17.18, and interaction diagram factor and minimum area of the steel, which is AS equal rho AG, rho equals 0.03 from appendix graph number 7. We find it from graph number 7, and after we find the rho, we calculate the AG, which is equal to 7.68 inches square. We use 10 number 8 steel. Actual strength of the column, which is equal 5 BU. After we finding the 5 BU, we compare it with the PU. If it is bigger than BU, then the design is okay. If it is less than BU, then the design it's not okay. Tie spacing, which is equal, we have two formulas for tie spacing, which is equal to 48 multiply tie bar diameter over 8, which is equal 18 inches, and 16 multiply 1, which is equal to 16. We take the less column dimensions, which is 16 inches. We use number 3 bars at 12 inches spacing center to center. And here the minimum size of the ties. This slide is just standards, and we satisfy all of the standards, so it's okay. And this is the cross section of the column that we calculate. Sorry for being fast, but I have limited time. Thank you.
Assalamu alaikum warahmatullahi wabarakatuh. I'm Sam Fadli. I'm talking about the design of footing, square isolated footing. The design of requirements. First, the depth of the foundation, 4.92 feet. The specific weight of the soil, 110 pound per foot cubic feet. Allowable soil pressure equals to 5,658 pound per square feet. Type foundation isolated footing. Column dimensions 16 by 16, and thickness of footing 24-inch. Depth of footing, effective depth equals to 90.5 inch. The load transferred to the footing will be the load from the column to the footing, and the self weight from the column under the ground level, which equals to 0.9303 kips. So the total load to the footing, PU plus PSW, equals to 54.5903. Footing and soil weight. We need to calculate the effective soil pressure, so we can determine the required area of the footing. The effective soil pressure equals to allowable pressure, soil pressure, minus the footing pressure minus the soil pressure, which equals to 5.0371 kips per square feet. So required area equals to the load of on the footing divided by the effective soil pressure, equals to 10.84. So we can choose the section 4x4 of the area of the footing. And we can calculate the ultimate soil pressure equals to the load on the footing divided by the area equals to 3.41 gibbs per square feet. The footing will be subjected to two types of shear, one way and two way, and we need to determine the depth for each type of shear. So we calculate the P0, which is the critical perimeter, equals to 142 inch, which is the perimeter around the column at the distance d/2 from the face of the column. We can calculate this equation, Pu2 divided by 5 multiplied by 4 square root of F prime C multiplied by P0 equals to 0.92, which is less than the assumed depth 19.5, which is okay, safe. Depth required for one-way shear, which is at the distance critical section will be at distance d from the face of the column. We can calculate the depth required by dividing Pu1 divided by 5 multiplied by 2 lambda square root of prime C by the width of the footing equals to 0.87 less than 19.5 inch. Okay. And flexible design, we can calculate the maximum bending moment, which is at the face of the column, by assuming it is a cantilever beam. We can use this equation. Mu equals W squared divided by 2. W equals to Qu multiplied by width of footing multiplied by the length from the face of the foot, the column, to the end of the footing divided by 2 equals to 12.12 kb per foot. We calculate Rn to determine the rho value. Find it 8.85, which is less 192.2, which indicates that rho will be less than the minimum, which is 0.0033, so we use the minimum value. We can determine the area of the steel by multiplying rho by the width and the depth. We get it 3.1 inch squared. Can use for number 8 bars at area 3.14 inch squared using ACI 318 table A.4. And this is the cross section of the foot.